In this lecture, we're going to learn how to generate hypotheses and theories. This is typically the third step in the process of doing research. We've already discussed how to identify a problem or a question and reviewing the literature. Now, it's time to start considering our possible answers. Let's start with theory. Theories are generalized explanations for what we observe in the world. They play an important role in driving basic research. Observation tells us what to expect. We all know that what goes up must come down. Theory helps us understand why that is the case. Now, research isn't always about building or testing theory. Sometimes we just want to observe or describe rather than explain or understand. Sometimes, as in action research, our goal isn't to explain broader patterns, but to find solutions for specific people, groups, or organizations. But a large swath of research is focused on explanation, and frequently, understanding why can help you apply ideas to new cases and events and even let you make predictions. Anytime you are interested in why or how things happen, or you want to fit an event into a larger pattern or trend, we're gonna want theory. Theories have to be tested by data. While you can use inductive reasoning to form theories from observation and data, there are dangers if we just stop there. It can lead to what is called data fitting. In other words, basing our theories on the data we have, which may not be comprehensive. Remember when we talked about how our personal experience is no substitute for research? It's the same idea. If you form all of your ideas based on your own personal experience, you're gonna have a very limited view. Likewise, we don't simply build theories out of the data we have and assume that they are true. Instead, we observe, we form theories based on those observations, and then we test those theories against new data. We also value parsimony in our theories. This is a quality drawn from the Occam's razor principle, that the simplest explanation is usually the best. Parsimony means that when everything else is equal, we prefer simpler explanations to complex ones. We want to maximize the story that a few variables can tell. If I can explain some outcome using just one or two variables, that's going to be considered a stronger theory than if I need 10 or 12 variables. But we don't want to oversimplify and lose the causal power of our theory. If the explanation really does require those 10 or 12 variables, then it's better to keep a complex but accurate theory than to go with a simpler but less accurate one. So how do you develop theory? Well, start by thinking systematically about how and why one variable of interest affects another variable of interest. Theory is often about unwrapping those causal mechanisms that get us from point A to point B. If I theorize that cats make people happier than dogs do, it's not enough to just say that they do and test that. I need to be able to explain why cats lead to greater happiness. I might argue that since they are easier to care for, they put less strain on their owners. Or I might point out that cats, once armed with a water fountain, food, and litter boxes, can be left on their own for a few days. That means a vacation costs less, since there's no need to arrange for a dog sitter or kennel. And that means either more money in my pocket or more frequent vacations, both of which might make me, a cat owner, happier than a dog owner. Let's take a different example. Democratic peace theory, which we've touched on previously, argues that democracies tend not to fight each other. They aren't less warlike than non-democracies. They just tend to resolve conflicts with other democracies without going to war. Now, this is an empirical finding that, with few possible exceptions, generally holds true from 1815 onward. But nothing I've said yet is theory. Theory requires an explanation of how or why this empirical relationship between type of government and likelihood of war might be true. Why is it that democracies tend not to fight each other? Many political scientists have focused their entire careers on answering this question. There are many possible explanations, but let me outline two of the more prominent ones. One explanation focuses on the nature of democratic institutions and how they restrain political leaders. The other explanation focuses on norms, that democracies as like-minded countries tend to promote less violent ways of resolving conflict with each other. Now, I am vastly simplifying here, but I hope you see the point. Understanding how democratic institutions or norms might make a democracy more or less likely to engage in war, that is the very essence of theory. And that theory helps us understand why a particular empirical finding in the data might be true. To develop your theory, first look to the literature. See what kinds of explanations are already offered and examine whether the evidence in the literature supports those explanations. Are there gaps that aren't explained? Cases that seem to contradict the general findings? Debates that aren't yet resolved? All of those are fertile grounds to spark your own ideas. Another way is to engage in some observation. At an early stage of your research, examining data can be a useful way to generate theories as well as hypotheses. Eventually, you will want to subject these theories and hypotheses to proper tests, but initially, you're going to need some knowledge on which to base your theories. One thing I like to do is to draw arrow diagrams. I put my outcome of interest, say, war between countries, on the right side of the paper. And then I start diagramming out possible factors that could affect the likelihood of war increasing or decreasing. I will draw arrows between these factors, linking them. As new factors arise through my reading of the literature or thinking through empirical puzzles, I put those on the diagram, trying to figure out how these factors might be related to each other. The more I read, observe, and test, the more refined my diagram becomes. The key is ensure that your theory helps answer your research question and it aims at explaining general principles, not just specific cases, and that it advances our understanding of the phenomenon of interest. Now that we've introduced the idea of theories, let's turn to hypotheses. Now, hypotheses are testable statements that provide the researcher's best guess at an answer to a research question. Hypotheses are typically derived from theories, although sometimes it works in reverse, and testing hypotheses helps us build theories. For example, I could hypothesize from our earlier discussion of democratic peace theory that countries with democratic systems of government are less likely to fight each other than they are to fight non-democracies. That is a testable statement. We could design a study that looks at the war habits of democracies and see who their opponents have been, other democracies or non-democracies. If we find that there's no difference in their opponents, that they're just as likely to fight other democracies as non-democracies, or that they're maybe more likely to fight democracies, that would actually disprove our hypothesis. Now, if in our study we find evidence that supports our hypothesis, note that this doesn't mean that we're automatically correct. We may be right, but we haven't proven our case. Let's take a moment and talk about that word, prove. I have a rule in my classes. The word prove is banished, exiled, not allowed under any circumstances. If a student uses that word on a paper, it gets a giant red no next to it. If the students say it out loud in class, I stop everything until they correct it. If they do it twice, I throw myself to the ground in a fit, and they can only resurrect me if they explain why I treat the use of the word prove like a literal blow to the head. Why does a single word bother me so much? Simply put, proving is not very scientific. In science, we set out to disprove, not prove. When you prove something to be true, that means it's pretty final and definitive. That's why in math they use proofs, and in legal courts they speak of proving guilt beyond a reasonable doubt. In many research areas, pretty much everything is uncertain and conditional. We are rarely 100% positive about anything. We find evidence that supports a theory or hypothesis or refutes it, but there is no single piece of evidence that can prove our ideas correct. So instead, we set out to disprove ideas. It's what we're left with, the ideas that have been tested but not disproven, that form the foundation of scientific understanding. So why is it that if we find evidence to support our hypothesis, we shouldn't assume that our hypothesis is definitely correct? Well, there are a couple of reasons. First, it's possible that it's only correct for whatever data we happen to look at. It might be that if we had more data or from different sources or over a longer time frame, that the results would be different. Our hypothesis about democracies not fighting, that comes out of the democratic peace theory, one of the more famous findings in political science. The data largely supports the hypothesis, but war itself is actually exceptionally rare. It might be that we just haven't had enough wars in the period following the American and French revolutions to really assess who fights whom. So our data might be incomplete, missing, or flawed. A second reason we can't just assume our hypothesis is correct is because there might be alternative explanations that account for the relationship we suggested. In our example, we did find evidence that democracies tend not to fight each other, but they have fought non-democracies. But maybe it's not the system of government itself that matters, but economic conditions. It could be that countries in higher stages of development are both more likely to be democratic and less likely to fight each other because of the impact on wealth and markets. Other scholars have suggested factors such as common national interest or use gender-based arguments to explain the democratic peace theory. I hope you can see how closely theory and hypothesis intersect. Theory, by increasing our understanding of why and how things happen, and sometimes the causal mechanisms underlying the why and how, can also help us assess our hypotheses and findings. A hypothesis without theory, it's like a birthday cake without frosting, incomplete, unappetizing, and likely to end up in the trash. Now, some research focuses just on developing theories, and that is fine. Who amongst us doesn't like to lick the frosting, even if there's no cake to put it on? But ultimately, if our goal is to advance knowledge or be reasonably confident that our ideas are correct, we need to examine empirical evidence. That doesn't always require a hypothesis to test. Sometimes we're looking for themes or describing our findings or engaging in critical analysis. Other times, we are doing research to figure out the variables that might play a role in affecting our outcomes of interest. You can't really write a hypothesis because you don't know what variables to use. Completely reasonable. Hypothesis testing might come later or not at all. So if your project doesn't lend itself to hypothesis testing, that is fine. But a lot of research does involve constructing tests to evaluate hypotheses. And having a hypothesis can be an advantage in that it provides guidance for our research. Just as a research question provides more guidance than a simple topic, a hypothesis can help guide you towards a specific research design and provide a framework for your analysis. So just in case that your research is focused on developing and testing hypotheses, let's talk about how to write a good hypothesis. There are some rules to keep in mind. First, in keeping with the idea that we are never 100% certain about anything, hypotheses are typically probabilistic. If we state a hypothesis in an all or nothing sort of way, there is no room for nuance, random chance, or exceptions. For example, consider a hypothesis that says that owning cats always leads to more happiness than owning dogs. Now, the dog owners amongst you are probably bristling. As a cat lover, this seems perfectly plausible to me, but all I would have to do is find a single person for whom that statement is not true, and my entire hypothesis is incorrect. So instead, why not hypothesize that owning cats is more likely to lead to happiness than owning dogs? Now, we're set up to evaluate patterns. When I find that strange dog lover, they no longer completely refute my hypothesis. Instead, they're a single data point that I will evaluate to determine larger patterns. If I find that 75% of my happier pet owners have cats, that would still support my revised hypothesis. For my less probabilistic hypothesis, the one that uses always, it'd be wrong from the start. 75% is still an interesting finding and worth knowing. So we write hypotheses probabilistically. That usually means using words like more likely or less likely rather than always, never, or will when we write our hypothesis. A second rule for hypotheses is that they are written about general groups or concepts, not specific people. So consider this hypothesis. My cat Xander is more likely to make me happy than my dog Obi. Do any of you really care which of my pets makes me happier? Probably not, or at least not more than idle curiosity or outrage over the implication that I might rank my pets. Xander is the cutest, by the way, of my 3 cats. But more to the point, would any funding agency want to give me money to conduct research on such a hypothesis? Would anyone want to publish my results? Would my boss care? No, of course not. Now, those same groups might care if I were able to say something more broad about cat and dog ownership. My boss is probably just tired of seeing my cat photos on social media. This is why hypotheses are written in a generalizable way. That is, in such a way that they apply to broad groups, not specifics. We write hypotheses about cats, about food, about general behaviors such as obsession, not about my cat Xander or what I ate for breakfast this morning or about how I might be obsessed with my cats. A third feature of hypotheses is that whenever possible, they should state a specific proposed relationship between variables. What this means is that your hypothesis should specifically state something you expect to find when you examine the empirical evidence. That's what allows us to design our research to create a strong test. We're testing whether or not the data supports the existence of this proposed relationship. If we don't state what that relationship is, our tests won't have any purpose to them. There are generally 2 broad categories of relationships that we look at. They're correlation and causation. In a hypothesis that focuses on correlation, you're stating that you expect to find a relationship of some kind between true variables. You might indicate what kind of relationship you expect to find. Do you expect that as one variable increases, so too does the other? Or do you expect that second variable to decrease? For example, consider our hypothesis that those who own cats are likely to have higher levels of happiness than those who own dogs. This states a specific relationship between 2 variables, type of pet owned and level of happiness. We're saying that people who fall into one category of that first variable, cat owners, are more likely to be happy than those who fall into that second category of the variable, dog owners. This is stronger than hypothesizing that pet ownership and happiness are related, which is less specific but purer form of a correlation-style hypothesis. So correlation looks at whether or not there is a relationship between 2 variables, and plenty of hypotheses focus on that. The second broad type of relationship is a causal relationship. In causal relationships, we're investigating whether or not one variable causes change in the other variable. We aren't just looking to see whether there are patterns in the values of 2 or more variables. We're looking to see if specifically change in one variable causes change in another. Our pet ownership hypothesis is actually a causal hypothesis. We're stating that pet ownership causes a change in happiness levels. It takes the idea of testing for a relationship one step further by claiming that one variable is the cause and the other the effect. We have language for this. When we're talking about our cause variables, The ones we think are affecting some outcome of interest to us, we call those our independent variables, and we usually refer to them by the letter X. In an experiment, our X is the variable we're manipulating. It's the drug we're giving to subjects in medical research. It's the characteristics of the name used on a fake resume in a study on racial or gender bias in hiring. In our study on whether type of pet owned matters in terms of happiness, it's whether or not you own a cat or a dog. The other type of variable, the outcome or effect, is called the dependent variable, and we use the letter Y to refer to it. This is whatever phenomenon we're studying, that thing that's changing, and we want to understand why it's changing. A lot of research starts by finding an interesting dependent variable and then thinking, I wonder why that is. Your independent variables, or X's, they're often the answer to that question. So in our pet ownership example, the Y is happiness. That's the outcome we want to explain. In our democratic peace example, the Y is whether or not states fight wars. In a study where we administer drugs for medical research, the Y is whether or not the medical condition improves. We're going to use this language of independent and dependent variables, X's and Y's, throughout the rest of the course. One final point before we move on. Keep in mind that at some point you should indicate the conditions under which you expect the hypothesis to function. It may be that the relationship you expect is only likely to occur for adults, or only for people in the United States, or only for women. If your proposed relationship is limited in that way, you're going to need to state that, either in the hypothesis itself or in your explanations. We have one more feature of a strong hypothesis, and that is it should be falsifiable. Now for this, we need Austrian-born philosopher Karl Popper. Popper argued that hypotheses must have falsifiability. That is, that they're written in such a way where they can be disproven. For Popper, falsifiability is so important, it's actually what distinguishes science from non-science. Now, if my hypothesis is that there's a giant monster living in a lake in Scotland, can that be disproven? Not really. Despite no evidence beyond a blurry photograph, plenty of people still think Nessie is out there. There's no definitive way to disprove her existence. So this is also why it's difficult to scientifically test religious ideas. Religion is about faith, not about proof or disproof. This is also why most research is actually testing what's called the null hypothesis rather than a hypothesis itself. Every hypothesis has a null hypothesis. A null hypothesis simply states that no relationship exists between our variables. That's it. There is no relationship between X and Y. And that's actually what we're setting out to disprove, because if we can disprove the null, that means that some kind of relationship does exist. Perhaps the one we hypothesized, or maybe something else that we weren't expecting. We're going to return to the null later in the course, but for now, it can be helpful to think about it. Even though we're talking about our research as testing a hypothesis, knowing that you're actually setting out to disprove a null hypothesis can help you sort why we disprove rather than prove. So that's 4 features of a strong hypothesis that you should consider when you're writing your own. That they're probabilistic, generalizable, they state a specific proposed relationship between variables, and they're falsifiable. Now, there are some templates that you can use to construct your hypotheses that follow these rules. They're not going to fit for everything you want to study, but they can be a good help to get you started. The first template is as follows. Value 1 of X is more likely to lead to value 1 of Y than value 2 of X. That's a mouthful, sorry, let's break that down. What this template is saying is that one category or value of a variable, X, is creating a particular effect on our second variable, Y, and that some second category of X is not having that effect. We're stating a specific relationship between the variables. X1 is having this effect, but X2 is not. X1 and X2 are the values on your independent variable. So if you're studying whether cat ownership leads to greater happiness than dog ownership, then your X is type of pet owned, X1 is cat ownership, and x2 is dog ownership. Your y is happiness. So let's say that we're using a very simple high and low happiness as our values for y. So if we plug these inputs into our template, this is what we get. Value 1 of x, cat ownership, is more likely to lead to value 1 of y, higher levels of happiness, than value 2 of x, dog ownership. Or simply, cat ownership is more likely to lead to higher levels of happiness than dog ownership. Our clear relationship is there, which gives us something to test. Also, by using variables, we're staying general. We're talking about general groups, not specific cats, dogs, or owners. It's falsifiable. We could find evidence disproving the statement. And it's also probabilistic. We're not saying that value 1 of x always leads to value 1 of y, just that it's more likely to than value 2 of x. That comparison across the independent variable, x, is clear. We're ready to test. Of course, sometimes we have more than one x to consider. In our example so far, we've been looking at a single x with 2 possible values, cat owner and dog owner. Sometimes we have multiple x's in play, each of them with multiple possible values. If I'm trying to explain pet owner happiness, for example, perhaps owning a cat versus a dog isn't the only factor that matters. Maybe in addition to type of pet owned, I want to consider how many pets the owner has. The more the merrier, right? You can always add more x's into that template. You might state that people who own multiple cats are more likely to be happy than dog owners or those who own just one cat. Now, that's not the only way to write a hypothesis, of course. I'm going to give you a second template, but this one comes with a caveat. It is easier to write, but you're more restricted in when you can use it. The second template is, there is a blank relationship between x and y. See, much simpler. Fill in the blank with positive, negative, curvilinear, or other descriptors of the relationship, and you are done. No messing around with values or anything else. Try, there is a positive relationship between the number of cats owned and happiness, or there is a negative relationship between the number of dogs owned and happiness. Let me actually explain those terms. A positive relationship is one where the 2 variables vary in the same direction. So as one goes up, the other goes up, and as one goes down, so does the other. A negative relationship is the reverse. The variables are going to vary in opposite directions. So as one goes up, the other goes down, and vice versa. Let's examine a sample hypothesis. I might argue that as you increase the number of cats you own, your happiness will increase. I may also be claiming that a decrease in the number of cats you own leads to a decrease in happiness, or just generally that your happiness level is directly correlated with the number of cats you own. These are all positive relationships. I might also argue that the more dogs you own, the less happy you are, and the fewer dogs you own, the more happy you are. That would be a negative relationship. Now remember, at this stage, we have not examined any evidence. We don't know whether or not these hypotheses are correct, even if they are striking you in a visceral way that is making you either nod your head enthusiastically or trying to reach through your speaker or headphones and shake me until I come to my senses. I'm using this example not because I necessarily think it's true, but because it makes for an easy way to understand these concepts. An emotional reaction means you really understand what I'm trying to explain. There are 2 restrictions to using the second template. The first is that these kinds of hypotheses really only establish correlation, not causation. If you just want to test whether 2 variables are related to each other, then this can work fine. If your goal is to figure out if one causes the other, however, this hypothesis style doesn't really clarify that for you. The second restriction is that for this style to work, your variables need to be at a certain level of measurement. That is, it needs to make sense that a variable can go up or down, or increase or decrease. Some variables we may want to study don't make sense in that way. As an example, take the variable marital status. Consider the traditional categories or values of that variable: single, married, divorced, and widowed. And now let's say that we think marital status is correlated with happiness. So we write a hypothesis. There is a positive relationship between marital status and happiness. Think about what that's saying for a second. Remember, positive and negative are not normative judgments. They're words we use to represent a type of relationship. This sample hypothesis claiming a positive relationship is basically saying that as marital status increases, so too does happiness and vice versa. That doesn't make sense. Remember, our marital status variable is defined as one of 4 discrete categories or values: single, married, divorced, and widowed. And a positive relationship means that as this variable increases, so too does happiness. What does that mean for marital status to increase? There is no ranking or numerical ordering of single, married, divorced, or widowed. Is divorced more or less married than widowed? It just doesn't work. To use this second template, you need 2 variables where increasing or decreasing makes sense. So we could change our marital status variable to number of marriages. Then our hypothesis would be there is a positive relationship between the number of marriages and people's happiness. From a hypothesis construction perspective, that makes much more sense. But we had to change our variable entirely to do this, which we may not want to do. If we're really interested in the role of marital status in affecting happiness, we probably need to use that first hypothesis template. So we could hypothesize that people who are single are more likely to be happy than people who are married, divorced, or widowed. Now, there are plenty of other ways to write hypotheses, so do not feel bound to these templates. But when you're just getting started, it can be really helpful to have a format to follow. So use these as a starting point. Before I conclude this lecture, I just want to point out that science in theory and science in practice can differ widely. I've told you today that as researchers, we set out to disprove theories and hypotheses, and that we design our tests based on our hypotheses. In the real world of research, though, this does not always happen. There are a lot of incentives in place to not do this. For example, it's much more difficult to publish negative results than positive ones. In other words, if your evidence confirms your null hypothesis and rejects your hypothesis, that's very important to know and exactly the kind of falsifying that Karl Popper would applaud. But it's not as sexy as results that support a hypothesis, and therefore it's much more difficult to acquire grant funding for such research or to get it published. It's also true that sometimes scientists will just run various models on their large data sets, and then when they hit on a finding, pretend that this was their hypothesis all along. Now, I don't advise this or support it as a practice. It can lead to data fitting, and it doesn't necessarily advance the state of knowledge. But it can be an effective way to get results that can be published. And for a lot of researchers, particularly academics at big research universities, getting published is one of their primary goals. Their careers depend on it. My caution to you is that there are strong reasons to follow the rules of scientific inquiry when it comes to research. Ethics demand it, and for many of the projects you're doing, it is just as important to know what doesn't work as what does. There are always going to be incentives to avoid or bend the rules. My advice, try to resist those incentives. Now that's all for now, and we're at the end of our section on the fundamentals of research. Next time, we will start digging into everything that goes into designing our research project.